Next up, we are going to have Jim Duffy and Brian Ho from Keysight Technologies, and they will present electric vehicle and EV supply equipment and test solutions. So I see Jim and Brian are in there. So as we get their slides configured and soon to display here, just hang on 1 second while they get them presented. All right, that looks good, Jim.
Very good, I'll commence. So what we're going to be discussing here today is wrapped around the charge discovery system and measuring EMC during a charging session. And that involves this instrument down here, or the equivalent of it, as I'll show momentarily, this white and red box here, along with our AC grid emulator and our DC emulators, which help as well, depending on what we're testing. And in this case, we'll be testing an EV, not necessarily an EVSE. And again, this is only a portion of the very comprehensive test solutions that we have for the EV platform, which include also a battery management system test, very comprehensive battery testing, no matter what level you are, power semiconductor characterization for the new wide bandgap semiconductors that are going into the inverters that are driving the traction motors. And with our DC emulator and our machine emulator, we can test that inverter, along with DC to DC conversion testing and lithium-ion self-discharge measurement testing. Okay, let's focus down here on the lower left corner. These are classic examples of charge discover testing. Here we're testing the EVSE, the charging station itself here on the left, with a high-powered CDS in the middle, and we're emulating the electric vehicle with a DC emulator. In this test, we're using our AC grid emulators to test the EV. We don't have a charging station. This grid emulator is emulating that with our high-powered CDS in the middle. These are called man in the middle. No, they're not. I'm sorry. We're emulating. There's not man in the middle, but the CDS in both applications is in between either the electric vehicle or the charging station, depending on what we're emulating. These are just classic examples. What we're going to focus on today is this particular unit down here on the lower left. This is our EMC series for this CDS. The one in the middle is our portable series for relatively low power applications, up to 1,000 volts and 300 amps continuous. But then when we push up to close to 600 amps and 1,500 volts, we need to cool these cables to handle that current for that duration. So those are the three models that we offer. We're going to focus more here on the EMC version down here in the corner. And that's what is shown here. This is what it looks like. It's an EMC optimized case for emissions and immunity testing. And the immunity of the CDS is rated up to 200 volts per M between 30 megahertz and 1 gigahertz. This is just an example in a chamber of how we might set up to test EMC with our CDS. In this particular example, we're showing a charging station being tested, for example. It could be other subsystems like an onboard charger or an actual EV in some situations. So speaking specifically to electric vehicle testing under these conditions, this is just a quick example of what the setup might look like. The quick schematic. A better understanding of this would be this particular slide here, where we go into the quick show of the general concept of how we can connect and implement our system in an EMC chamber, whether we're testing a subsystem, an EV, charging station, it doesn't matter. The first interface, of course, here is the connection panel up here, A, where our DC power enters the chamber via high voltage plugs mounted to the panel. Now, this connection panel would be lab specific and tailored specific to the needs of the test and in the lab. Next, those same DC power lines go through what is known as a line impedance stabilization network, an LISN, to the adapter, which is directly connected to, while the communications cables are, excuse me, from the EMC CDS unit itself are routed in shielded bus cables from Phoenix Contact. And finally, of course, the EV charging adapter connects to the EV itself, and we're ready to test. That's just a quick overview on a schematic level of what it would look like in that environment. So speaking of emulation of either the charging station or the EV, we have our regenerative power systems that we show here on the left side. We have 5 kilowatt to 30 kilowatt units that can be racked up and extendable to over 200 kilowatts. These operate in 2-quadrant mode as a power source or as a regenerative power load. So while we're going through a charging session and we're emulating an EV, for example, we use these as loads, but they're regenerative. So we're recovering 90% of the power that isn't wasted, and we're converting it from DC back to very clean 3-phase AC that can be used on the charging side, for example. So this keeps operating costs low, and we're not having to deal with dissipating a lot of heat. Also over here on the right are our AC grid emulators, which can again emulate either a charging station or an electric vehicle. They also have a DC option where they can act as these regenerative power systems. So a lot of versatility here in this particular unit. And next slide shows the different models that we have. We have both 600 line-to-line models along with 1200 volt line-to-line models as well, along with their DC output ranges for the 5 different models. So again, very versatile here. We can act as an AC grid emulator or a DC source and load. Okay, so when we get to higher levels and we need to either provide this as source or as load, we have our bigger DC emulators where we can go up to 1,000 volts currently and up to plus or minus 600 amps and 300 amp increments. Individually up to 360 kilowatts, but when parallel together, we can get up to a megawatt. And as we look at current market trends, we're seeing more of that demand. Again, on the discharge cycle, when it's acting as a load, we're 90% efficient in recovering that energy where it can be reused. Now, this is our Charging Discover test software, and it includes a wealth of features to make testing as easy as possible. The user interface is modular and resizable, featuring a measurement graph with user-selected traces being plotted in real time during tests. In addition, there's a system overview showing overall operation status at a glance and a test log showing the communications between the DUT and the CDS in real time. We also measure and log the attenuations levels for communications IO at the start of each test. All of the test data, whether you graph it in real time or not, is available to be exported after each test to a variety of file formats to make post-test analysis easy for you and all of your colleagues. So setting up the test is also easy, with the ability to create your own device of emulation DOE profiles for both EV and EVSEs in the software. And for advanced users, there even is the option to program your own test sequences. And these are examples, these screenshots are examples of what you can monitor as the charging session progresses. And this user interface is one of our best features of our CDS test solution. especially when you're trying to find those interoperability issues during a charging session. You know, you pull your EV up to a charging station, a charging session commences, it lasts 5 minutes and stops. Now, why did that happen? Is it the EV's fault? Is it the charging station's fault? Is it both their faults? This device is expert at finding those interoperability issues. Any questions?
So again, we have a QA button on the bottom of your Zoom interface. If you have any questions for Jim, why don't we go ahead and take those now, and we can address them. All right. I guess we didn't have any burning issues on that section. I think Jim is going to turn it over to Brian next. So,
Brian, do you want to bring up
Brian?
your portion of it, or I can step through these slides for you?
I'll bring it up.
Okay.
Can you see my screen?
Yes.
All right. Hi, everyone. My name is Brian Ho. I'm the RF Solutions Engineer at Keysight Technology. Today, I want to talk about the N9048B, the PXE EMI receiver, and the need for speed in regards to EVAEVSE testing. Before we go any further, let's kind of review why we need to do EMC testing. With the electrification of the vehicle, as well as the autonomous vehicle technology moving forward, vehicles will now rely heavily on sensors rather than human input. That being said, if any of these sensors were to fail, a lot of times it can cause potential harm to the driver, the passengers, and the people around them and the environment. So it's very important to do these EMC testing to weed out all the problems so that we can mitigate all these problems. All right. That means, yes.
Hey, Brian, sorry to interrupt you here. We're having a little bit of an issue with your audio. I don't know if there's a slight adjustment that you can make.
Okay, 1 second. Can you guys hear me better a little bit now?
That's much better. Let's go with that.
Sorry, it must have been, I apologize. Okay, moving forward. So there are some challenges for EV testing with regards to EMC. We can break it down into three. The first one is performance, the second one is speed, and the third one is usability and scalability. Regarding performance, for EV testing, you need a high sensitivity, wide dynamic range, and superior accuracy that is reliable and repeatable. Regarding speed, a lot of regulatory tests require fast testing and measurements to avoid overcharging in the battery and delays in resetting the test. Passive scans with time domain scans, or TDS, and event time domain scans allow much faster analysis and testing, which in turn shorten measurement times without compromising accuracy. This helps your product go to market much faster. The third challenge is usability and scalability. A lot of these tests require technicians or even engineers to do, so it has to be easy to use for those technicians and engineers. Another one is an ease to upgrade for EMC testing in the future, as technology is always improving and always changing, so there will be changes to the specification. Now, Keysight has a receiver called the N9048B, the PXE EMI receiver, to address this issue. Before going forward, I want to note a few things. First thing is, Monolith Power actually has a few of our receivers in their lab, and all the benefits that I'm going to talk about today in this presentation, you can actually see and experience at their lab when you test there. So it is very beneficial to understand what type of equipment they have, and just wanted to show you this equipment. Before going further, I want to try to introduce our equipment. This equipment has a bunch of frequency ranges from 1 Hertz to 3.6, 8.4, 26.5, and 44 gigahertz. The receiver is fully compliant with EM standard sets of CISPR, MIL standards, and ANSI. Regarding performance, it has very superior amplitude accuracy as well as industry-leading sensitivity. We do have extremely fast time domain scans and what we call wideband accelerated time domain scans. We also have gapless signal capture with time scans up to 350 megahertz. Another thing is it is touchscreen and it is a Windows OS, so it can be upgraded relatively easily. For the user interface, we do have simplified predefined scan tables, built-in limit lines, as well as automated testing capabilities to make it easy for the users as well as the technicians. Another very cool thing is we do have a lot of debugging tools. So a lot of times there is failures when you test. We have the ability to look into those failures. We do have spectrum analyzer built in. We do have real-time spectrum analysis, spectrograms, and other things that can help you debug on the spot if there is an error. Now, we mentioned time domain scans and light-headed time domain scans. What exactly is that, and how does that make testing much quicker? Well, with a standard receiver, they usually do what's called a step scan, where they have a filter that steps at each frequency, dwelling each frequency and measuring. This can take a lot of time because depending on the specifications, some might require you to dwell at a frequency at 1 second before moving to the next, or maybe less than that. But it does take a long time, especially if it's a bigger bandwidth things. Now, with what we call time domain scans, rather than just have a filter, we have multiple filters measuring at the same time. This gives us more of a bandwidth of measurement rather than a frequency of measurement. So you can measure instantaneously for our TDS scans at 59 megahertz bandwidth. Now, if you think about that, if you were to dwell at 1 second, it takes chunks out of these measurements, even if it's big bandwidth. Now, we have another technology called accelerated time domain scans. Now, this is has much more bandwidth. It is about 6 times the bandwidth of that, which means it would be 6 times faster. Now, it's really hard to imagine this. So let me show you the next slide, a video of both the standard time domain scan and the wide time domain scan. As you can see, the wide time domain scan already finished within the 6 seconds, and we're both measuring CISPR band CD, 30 megahertz through 1 gigahertz, positive peak detector, 100 kilohertz RBW with 1 second dwell time. If this was a standard receiver, it would take a lot more time than even the standard time domain scan, which is still scanning at the moment. So even from the standpoint of looking at like standard time domain, even advanced time domain, it does save you a lot of time in your scans. I'm going to just let this finish quickly before moving to this next slide. All right, it's done. So you can see it's still relatively slower than the wide time domain scan, but much faster than if it was to do a receiver that stepped. Now, just to put into perspective, here are some of the times that we have for different measurements, just to put into perspective the PXE can do. But this is not really relevant to automotive, so I'm going to give an automotive example in the next slide. I'm sure a lot of you are familiar with CISPR 12 or CISPR 25, which is what a lot of the EMC tests are based upon, the vehicle level test or even the sub-assembly test. We're going to use that to show, we're going to test according to that to show you the time difference. In this slide, you can see that we're going to do 2 different measurements. One is measuring one position, 30 megahertz to 1 gigahertz with a positive peak detection, 1 second dwell with RBW 120 kilohertz. And the second one, we're going to do 4 antenna positions, which we have to physically change the position of the antenna and measure. So we'll do left side, right side, vertical orientation, horizontal orientation. In a standard step scan for the 30 megahertz to 1 gigahertz test, it will take about 9 hours to do because, as I said, this is a bigger bandwidth and it's dwelling at 1 second per frequency. With time domain, we can get that within 50 seconds. What's even more impressive with accelerated time domain scans, we can get it to 6 seconds. Now, if you look at an antenna position where you have to switch the antennas physically, you get about 36 hours for a step scan versus a 200-second scan with the time domain scan, or impressively, a 24-second accelerated time domain scan. Now, that being said, this does help make the testing time less slower. But what happens if you have an issue? Well, we have a lot of other tools that can be very beneficial to debugging and actually finding the issue. One of the tools that we have is called the real-time scan. And on the screen, you can see that there's 3 windows, the top, middle, and bottom. At the top, we have the frequency domain. In the middle, we have spectrogram, and the bottom, we have the time domain. This is a very full function that I think is very helpful because One, we have up to 350 megahertz bandwidth of instantaneous measurement. And we can also have 3 different detectors, peak, quasi-peak, EMI. And what I think is very helpful is if you see an issue in the frequency domain at the very top, you can actually put a marker at that frequency and actually look in the time domain at the bottom and see what's going on in the time domain. For example, if there's harmonics that is pulsing and you see a peak, it might be easier to look in the time domain to see, okay, this is repetition at this time. Maybe it is a clock from a CPU. So this is a very handy tool that we have in this PXC. Another cool tool is we have real-time scans. A lot of times when you do a traditional scan, you sweep across it slowly, step sweep. So a lot of times if you're out of sync with the signal, you might not even see it. But if you're to see a real-time scan, everything is seen instantaneously and you can actually see the issues even without having to synchronize your timing of your receiver. Another cool choice is we do have a lot of different choices of measurement, Toyo, Nexio, ETS, TDK. Again, monolithic power does have a receiver, so if you do want to see the benefit of this, I would recommend going to them and seeing what testing can be done to minimize the time you take to do these tests. Any questions?
Okay, again, the Q&A button is listed or is at the bottom of your Zoom webinar interface. Go ahead and pop down there and you can type in any questions for Brian. I would like to thank Keysight for joining us today and helping us with our EMC Insights and Solutions event.